Welcome to this explainer. You know, we constantly hear about the latest software models, the massive GPU clusters, the whole shebang. But today, we're diving into the invisible, physical hardware, and the hidden supply chains that are absolutely critical to powering the global AI boom. We're looking at the actual infrastructure making it all possible, and more importantly, a looming physical crisis that could literally stop AI in its tracks.
Okay, let's just quickly check out our roadmap for today. First, AI hits the copper wall. Second, bringing light to silicon. Third, the three topology models. Fourth, the manufacturing bottleneck. And finally, the battle for control. Section 1, AI hits the copper wall. The existential threat to scaling AI data centers. We really have to start here with this foundational crisis.
Because right now, scaling artificial intelligence isn't just about raw compute power anymore. It's about the physical transit of data. We're slamming headfirst into what engineers call the copper wall. As we try to push massive terabit-level speeds through traditional copper wiring, we just hit the ruthless limits of physics. First, there's signal attenuation, where the electrical signal just degrades over incredibly short distances. Second is thermal density. Pushing all that data generates immense, localized heat bottlenecks. And third, the sheer power consumption needed to force electrons through copper at this scale is honestly threatening to completely eclipse the power needed for the actual computing itself.
To put that into perspective, consider this massive efficiency gap. We're currently transitioning from legacy pluggable optics, which use these incredibly long electrical traces across circuit boards, to co-packaged optics, or CPO. By completely cutting out those power-hungry electrical paths and bringing the optical connection directly to the chip, CPOs can achieve up to a 70% reduction in power consumption. That's a massive paradigm shift. It's literally like trading in a gas-guzzling truck for a hyper-efficient EVE overnight.
Section 2. Bringing light to silicon, the paradigm shift from electrons to photons. So, how do we actually bypass this copper wall?
Well, to make this happen, we have to seamlessly convert electrons into photons, right there, directly on a single surface. It's a totally fascinating sequence. Step 1, your main processor, the XPU, generates the electrical payload. Then, step 2, an electronic circuit conditions that signal. Step 3, a photonic circuit jumps in to act as the translator, turning those electrical signals into blazing fast pulses of light. And finally, step 4, an external laser provides the continuous wave of light needed to actually carry all that data. Now think about that external laser engine for a second. It absolutely has to be kept physically separate from the massive heat generated by the core processor in the center. If it gets too hot, those sensitive optical components will simply fail. So thermal management here isn't just an afterthought. It's an absolute beast of an engineering hurdle.
Section 3. The three topology models. Architectural blueprints and physical trade-offs. Let's look at the actual engineering blueprints system architects have to choose from. First up is Model A, the switch-cpo integration. Here, you tightly cluster the optical engines in a ring around a central switch on a high-density interposer. This design keeps the electrical channels ultra-short, which drastically lowers power consumption. But the massive trade-off, you get absolutely zero upgrade flexibility. The switch and the optics are permanently tied together.
Next, we have Model B. This model is wild. It bypasses external PCIe or Ethernet limitations entirely by connecting GPUs directly to one another via fiber ribbons. This gives you the absolute minimum latency possible, basically enabling radical new supercomputing clusters. But man, it introduces extreme package costs and massive manufacturing yield risks, mainly because you're trying to perfectly combine the processor, memory, and optics all into one ultra-dense package.
Finally, Model C. This acts as a really pragmatic intermediate step. It utilizes a physical thermal break, keeping the main processor physically isolated on its own package, with the laser module completely detached at the edge. This protects the main chip's manufacturing yield and lets you upgrade the optics independently, while you still capture those major efficiency gains over legacy systems.
So, bringing it all together, there's no silver bullet yet. Architects face a super stark choice. Do they minimize immediate financial and manufacturing risk with the modular approach of Model C, or do they just embrace the extreme thermal complexity and yield risk of Model B to unlock the absolute performance ceiling we're going to need for next-gen AI?
Section 4, the manufacturing bottleneck. Surviving the submicron assembly gauntlet. Because, designing these sophisticated optical packages is one thing, but actually making them, that is where the real ecosystem leverage and the true margin is generated. 10,000 plus. Just let that number sink in for a second. This represents the absolute explosion of microscopic alignment points required per module as we scale up into Generation 3 architectures. We aren't just soldering metal together anymore. We're trying to perfectly align microscopic glass to silicon. To hit those 10,000 alignment points, manufacturers have to rely on a process called robotic active alignment. Unlike traditional electrical soldering, the lasers actually have to be powered on during assembly. A robotic system fires the laser, measures the light output, and micro-adjusts the glass fiber to the silicon waveguide with sub-micron precision until it hits absolute peak signal. Then, they lock it in place with UV epoxy. If it's a fraction of a millimeter off, boom, catastrophic signal loss, game over.
And because this entire advanced manufacturing gauntlet relies on perfectly stable light sources, the supply of high-quality continuous wave lasers has become a rigidly constrained bottleneck. These intense precision demands are driving a massive re-rating in the prices and the yield trends for these highly specialized components across the whole industry.
Section 5. The battle for control. Ecosystems, hyperscalers, and the ultimate AI factory. Let's zoom back out to the multi-billion-dollar macro level. The world's biggest tech titans are literally going to war to control this critical infrastructure, and they aren't all taking the same path. They are actively fracturing into different strategic camps, fiercely navigating this optical transition to try and avoid total vendor locking. The divide is incredibly stark. On one side, companies like Google and Meta are acting as independent builders, directly contracting with silicon photonics foundries and laser suppliers to build their own custom proprietary optical networks. On the flip side, you have NVIDIA pushing a tightly coupled end-to-end turnkey solution where they provide the compute, the network, and the software all as one massive integrated AI factory. And honestly, NVIDIA isn't taking any chances here. To permanently dominate data center networking, they are proactively investing over $4 billion to essentially buy up the capacity of the critical supply chain. By locking down the laser bottleneck and advanced 3D packaging capacity, their goal is to secure their own optical fabric and potentially lock competitors out of the supply chain entirely. Ultimately, this dictates whose hardware runs the everyday AI tools we all rely on. Which leaves us with a really profound final question to consider as the global tech industry fundamentally realigns around this physical hurdle. Because as the copper era officially ends and value drastically shifts upstream to advanced optical packaging, data transit has definitely surpassed raw compute as the ultimate choke point. The permanent shift to glass and light is already here, so the only question left is who will master these sub-micron physical connections to become the ultimate gatekeeper of our AI future?